Hello, everyone. Welcome to another topic in chemistry. Our topic today is energy and light calculations. If you are watching this video the first time it was assigned, it is March 29th, Unit 7, Day 4. If you're watching this video for any other reason or at any other time, I welcome you and I'm excited to tell you about energy and light calculations. Go ahead and set up your focused note page. The essential question we will be answering in this lecture is, how do I calculate the energy of a moving electron? So this video lecture assumes you already know a little bit about how light is produced, about electrons starting out their ground state, they gain energy and move up at least one level, they fall back down and release energy, and that's when wave patterns are shown, and those waves have wavelength and frequency, and we can measure those things to eventually calculate the energy of a moving electron. So that's kind of where we are going with today's topic. Let's get into it. So we're going to be calculating different things about light. So really, we're calculating frequency or wavelength of a wave. If you know one, you can find the other, and eventually that will be related to energy. Frequency, just to review, is how often a wave repeats per second. And here's the official equation. C equals what looks like V, and then this is the Greek letter lambda. So here's what everything stands for. V is your frequency, so how often the wave is repeating, and it's measured in hertz. So the symbol is Hz. A hertz is really how many cycles per second, or just 1/2, or second to the -1. So all of these things mean the same. So if you see any versions of these on a number, you know that that's referring to frequency, how often the wave is repeating. Wavelength, as we've mentioned before on like the first day of this unit, is really literally the length of the wave. But what we mean by length is when the wave repeats itself. But because it's a unit of length, or because it's a length measurement, we use units like length, like metric, meter kinds of things, right? So lambda is the wavelength symbol, and we're going to put it in centimeters instead of nanometers or meters or anything else, because in this equation, we are using c, the constant speed of light, which is 3.00 times 10 to the 10 centimeters per second. Now, obviously, you could change this and not be centimeters per second, but the one I'm giving you is in centimeters per second. So if your wavelength then needs to also be in centimeters, so those units will cancel. And then you'll end up where you can either calculate frequency or you can calculate wave. But these two things are related to each other, and they're opposite or inversely or indirectly related. If the frequency is really high, like going really, really fast, the wavelength is really small, short wavelengths, because that multiplied together needs to be the constant speed of light. If you have a really, really slow frequency, that means that the wavelength must be really long. It's not moving very fast. So those two things multiplied together would give you the constant speed of light. Let's try this. So if we know the wavelength, you can find the frequency. If you know the frequency, you can find the wavelength. Let's do green light. Green is kind of a nice, pleasing color. So the wavelength of green light equals 512 nanometers. Now, there is a little range depending on the color of green, brighter green, darker green, green closer to like yellow, or green closer to blue, but in the middle is 512 nanometers. What is the frequency then of green light? Well, our equation is C equals V lambda. C is the speed of light, V is frequency, lambda is wavelength. That's what we were given. So then we can do some algebra and solve for frequency. All right. So we know that the speed of light is 3.00 times 10 to the 10 centimeters per second. Lambda was given in the problem. Wavelength is 512 nanometers. We're trying to find frequency. If we do a little bit of algebra, we can say that V equals C over lambda. So again, we just did algebra on this problem to solve for frequency, because that's what the problem is asking for. We plug in the two things we know, the speed of light and the wavelength, but wait a second. This is in centimeters. Sorry, I know that's a little hard to see. It's easier to see it over here. This is centimeters per second, and this is nanometers. We can't just do this division. The units won't cancel. So we've got to do some conversions, dimensional analysis. We can do this. It turns out that 1 meter equals 10 to the ninth nanometers. Nanometers are really small. 10 to the ninth fit in 1 meter. Think of like the length of a meter stick. 10 to the 9 nanometers fit into that. So what I can do is I could go from nanometers to meters and then meters to centimeters. That would work. So I'm going to set it up like this. Speed of light doesn't change because that's our constant. That's our centimeters. So 512 nanometers divided by 10 to the ninth nanometers times, and then over 1 meter. Nanometers cancels. Meters to centimeters. There's 100 centimeters in 1 meter. Meters cancels. I'm left with centimeters. Centimeters and centimeters cancel. I'm left with per second, or second to the -1. That is a unit of frequency. That's hertz. So that works out. So go ahead and pause the video and do your calculations. See if you get the same answer I do. Ready? Pause the video. Come back when you're ready. All right, how'd you do? So when I do this, I get a calculator answer like this. So just making sure you're typing all this stuff in correctly, dividing by numbers on the bottom. So that's really this number, and then it's divided by this, and then also divided by this, and times this, right? So it's a tricky, like this bottom part. You just got to be careful the way you type it in. This is the calculator answer, but we got to do sig figs. Our given numbers, this has 1, 2, 3. This has 1, 2, 3. So I can keep 1, 2, 3. I look at this number for rounding, which it does. So my answer is 5.86 times 10 to the 14th hertz. That's what I got. And that's also what my presentation tells me is the right answer. So check your math, check your algebra if you made any mistakes. Mostly this is just punching it into your calculator correctly. But this is the frequency of green light. So that's how we use this calculation. All right, go ahead and do a level 1 type of question, something straightforward. What is the equation for the speed of light? That would work, right? If you need ideas for Costa questions, remember there's a Costa question guide on Schoology. Come on back when you're ready. Here we go. Let's talk a little bit about energy now related to waves and frequency. So we've talked before that electrons start at their ground state, their fixed energy level where they start, and they can only jump to a different energy level if they give off, emit, or take in, absorb some quantum of energy. And a quantum is really just a specific amount. And that's what we're going to do next. We're going to calculate that quantum of energy. So when an electron moves up 2 levels and then falls back down 2 levels, how much energy is it actually giving off? Or if it needs to go from energy level 6 to energy level 2, how much energy would it need to release? That's what we can calculate now. So our new equation is E equals hv. Well, E you can probably predict is energy. V we just saw in our previous equation is frequency, so we already knew that one. H is a constant, so established by a guy named Maxwell Planck, who did a whole bunch of experiments on different wavelengths and frequencies of light and how much energy they produced. And so we have this constant, 6.626 times 10 to the negative 34 joule times second. Well, think about that. If I put this constant in for H, that means I'm going to multiply this by some number of frequency, which is hertz, which is 1 over second, right? So really, you're going to take joule seconds times over seconds. So seconds will cancel and joules will be your unit of energy. So that works. All right. And then we see that frequency and energy are directly related. If the energy is high, the frequency would be really high, meaning it was moving really, really fast. And so that makes sense because if you're moving fast, you would need more energy, even if you're a wave. And then opposite, if the energy is low, the frequency would also be low because it's not moving as fast. Those waves aren't repeating as much per second. Let's try this. So what if I said, what is the energy produced by the moving electrons creating a radio wave for the radio station at 102.9 megahertz? Now, this is real stuff. So you might have heard that, oh, if there's energy moving, that can change your cells, and that's dangerous. We got to be careful with those energy. Well, let's figure out how much energy is actually produced by radio waves. And this is a radio station that we happen to have here in Minnesota. 102.9 megahertz is how that's measured. Well, let's try it. We just learned that E equals HV. Megahertz is a unit of frequency. Okay. Planck's constant is always given to us, but the units do have to be match seconds. And megahertz would not be seconds. That would be like 1 over megaseconds, right? Think of it that way. So here's what we need to do. Here's our constant, H, so Planck's constant. And then here's my frequency, 102.9 megahertz, but mega is like 10 to the 6th, right? There's a lot of regular hertz fit in megahertz. So 10 to the 6th hertz equals 1 megahertz. So megahertz will cancel. Remember, hertz is really 1 over seconds. So then you really end up with joules seconds times 1 over seconds. So seconds cancels. So really, you just got to multiply all those numbers and you'll get energy in joules. So this is what our calculator says the answer is. You can see it's pretty small. Oh, we got to do sig figs though. So I can keep 1, 2, 3, 4 from there. 1, 2, 3, 4. So yeah, look, and this is a definition. So I can keep 4 sig figs. 1, 2, 3, 4. I look at this number for rounding, which it does not. So those chop away, and I get 6.818 times 10 to the negative 26 joules. A very, like an unbelievably small amount of energy, which is good because radio waves are all over the place. If they were high energy, that would be super dangerous to be around because it could cause problems with our cells. So that's a good thing. So now we proved it. Oh, it is a really, really, like so ridiculously low amount of energy, but it's enough energy to produce a wave that we can then use a radio station to hear. And then that's the entertainment piece of it. All right. So that is produced by electrons moving to cause that radio wave to send out through space. And then our receiver, our antennas can collect it. And then it turns it into sound that we can hear, not something we can see. All right. So those are the two equations. We've got the C equals V times lambda. So speed of light equals wavelength times frequency. And E energy equals Planck's constant times frequency. And you can sometimes mix and match those equations as well. All right, going into a level 2 kind of question. Pause the video. You could make up a different kind of calculation problem or a compare and contrast. But go ahead and pause the video. Think about the notes so far. Come back when you are ready. All right, so the last piece I just want to connect with it is the quantum concept, which is electromagnetic radiation. How does that fit into frequency and energy and wavelength? So a radio wave, like we just calculated, is low energy. And that's because the wavelength is really high, a really stretched out wavelength, and the frequency is really low. It doesn't repeat itself very much. And then through the electromagnetic radiation spectrum, it just goes more higher and higher and higher and higher and higher, eventually till cosmic rays, which would be our highest energy, our highest frequency, and our lowest wavelength, because it's a really short wavelength. It repeats itself very many times in a certain amount of times, like seconds, like hertz. And so high frequency, high energy, low wavelength. All right, go ahead and pause the video and do a level 3 type of questions and then a summary that answers our EQ for today. The level 3 would be something that's like a predict or imagine kind of thing, or defend. Chance to kind of process those notes, see if they make sense. Come on back when you're ready. All right, that brings us to the end of our Unit 7, Day 4, I believe. I apologize. I think this is a mistake. It should be Day 4. Doesn't matter. The point is we're done with today's topic. So finish any CASA questions and summary for today's notes. And then there are some unit practice problems. They're in the Week 2 Schoology folder. You put the answers in the back of your notebook. You can check the answers. It's immediate feedback. See if today's notes made sense. If you are watching these notes during the actual class it was assigned, let me just do some other class reminders. Flame test lab report should be done. If you need any help on it, make sure you get some help on that. Finish any other missing work. I'm caught up on grading, so if Schoology says it's missing, it means it is. So get that turned in. And then just a reminder about my office hours Monday through Thursdays from 2:15 to 3:15 on Zoom, and from Fridays from 1:30 to 3 on Zoom if you need any extra help. Thanks so much for learning more about light math with me. See you next time.